Okay. So last time I finished with talking about the hyperbolic metric, which is so it is actually y square in the denominator. So this is a Riemannian metric. Riemannian metric on the upper half space, which means it is at each point of H, you have a tangent space. And this gives an inner product. So how do you interpret this? How to interpret? So pick any point in the upper half space. So the tangent space at P, this can be identified with R2. So when I say this is a Riemannian metric, I should give you this should give you an inner product at each R2. So for each point, I should give an inner product on this. So what is the inner product right now? So first of all, how do you specify an inner product?
कार्तिक
Yeah.
हाँ स्क्रीन वापस शेयर करेगा मेरे स्क्रीन दिख नहीं रहा
ओह सॉरी बाकी को दिख रहा है क्या?
Yep. Yes.
एक मिनट दिख रहा है अभी?
ठीक है मेरा शायद से नेटवर्क प्रॉब्लम है कोई नहीं
हाँ ठीक है
दिख रहा है ठीक है दिख रहा है
ठीक है तो how do you specify an inner product? So R2, it is R2. So suppose E1 comma E2 is the standard basis. So to completely specify an inner product on R2, we just need to know these three values, right? So our metric was okay. So now x comma y act as coordinates for H2. Sorry, like upper half space. By this I mean like H is covered by a single chart. So whenever your manifold is covered by a single chart, we can talk about metrics like this. Like whenever you see this, this means you can only talk about this when there is only one chart. Okay. So what are the inner products now? So at each point, the tangent space is R2, and I will take the standard basis there, and I need to specify these values. So this value will be a coefficient of dx square, which is just 1 by y square. This is coefficient of dy squared, which is 1 by y square again. Sorry, y naught squared, because p was taken to be x naught comma y naught. Then this is coefficient of dx dy, which is 0. So this is how you specify a metric, an inner product on the tangent space. Okay, so that is the Riemann metric. For now, we will forget about all the metrics. We will go back to something else. We will talk about so forget about all the metrics. I will just talk about the Riemann sphere now. So what is the Riemann sphere? It is just the complex plane union one extra point, which will be called infinity. So we will also give a topology on this. So I will, to give a topology, I need to specify what are all the open sets in the space. So call the following to be open sets. So if you take any U subset of C, so any open subset of C will be called open in C infinity. Next, all sets of this form. So you take any compact set in the complex plane, you take its complement and add in the extra point. That will also be an open set. So for example, if this is your complex plane, your closed set you take to be this solid disk here. Like, then when you take the complement of this, you'll get everything on the outside plus infinity. Okay, so that will be an open set. So basically these are like these second kind of open sets. They are like open sets around infinity. Okay, so now let's talk about the stereographic projection. So stereographic projection for S1. So for S1, the stereographic projection looks like this. So this is the real line, and you have this unit circle over here. Take this northernmost point, then I will give a correspondence between the S1 minus this point to R. So that will go like this. You draw a line like this, and this line intersects the circle ones and the real line ones. So the map will take this point to this point. Okay, same goes for things over here. The map will take this point to this point. So basically it's a map from stereographic projection is a map from 1 minus. Okay, so this will So this will be a homeomorphism, which I will not prove. So what did we get right now? We got that if you take S1 and take out one point, you get R. So you would think that if you take R and add another point, you should get S1, right? Given like, given you make the topology right, like give a right topology on this, you will get this. So what was the right topology to give here? So you take the real line, you take all open sets in the real line, call it to be open. Then there will be more open sets. So let me call this infinity. More open sets, which will be like neighborhoods around infinity, which is like you take any compact set in the, or take like a closed interval in your real line and take the complement of that. That will also be an open set in your new space. So your new space R union this new point will have the same topology as S1. Okay. So in a similar way, we can do this for S2, where you have a sphere, then you have the R2 plane. So you take your north pole and you take your north pole and draw a line through any point. It will go hit the R2 plane only once. So then again, I will tell the mapping is like, okay, similar for this place. Mapping will be like this. So arguing similarly as previous part, you get S2 minus the north pole to be homeomorphic to R2. And similarly, if you take R2 union a point, which I'll call infinity, it will be S2. Okay. The topology given here will be the topology I told for C infinity. So R2 you can think of it as C. Okay. This happens to be C infinity. And using the topology I specified, this will be homeomorphic to S2. So when I say this, when I say this union, when I call it a Riemann sphere, it is actually a sphere. Okay. So now, what do we do next? We can, since we have a topology, we can talk about continuous functions. I will just give examples. So f of z going to z to the Rn. So polynomials are on C infinity are continuous functions. So this kind of inversion 1 over z map, this is also continuous. Of course, adding constants is also a continuous function. So this az plus b that is also a continuous function. I will use this later on, right? Not right now, but just keep these in mind. So now we will talk about circles. I will talk about circles in C infinity. This is again a new definitions. So C infinity is made of C union a point. So circles in C infinity will be, take all circles in your complex plane. Those will be circles by definition. And also take lines in C and add the point infinity to it. That will become a circle in C infinity. Okay. Just to note, so all circles, they are homeomorphic to S1 because circles in C are homeomorphic to S1, and lines union a point, as I showed using the stereographic projection, it will also be S1. Okay. So this is again a side note. It's just a note. So because these circles are S1 by Jordan Brouwer, C infinity is so every circle splits C infinity into two disks. Particularly, R union, R is a line in C, R union infinity is a circle. So this R union infinity will split C infinity into two disks, which will be so R. So if you take out R union infinity from C infinity, you will just be left with C minus R, which is just the upper half plane and the lower half plane. So what I'm trying to say here is the upper half plane is homeomorphic to a disk. Okay. Okay. So next, we will talk about equations. So what are the equations of a circle? So circle in R2 is this, right? If I want to convert this into complex coordinates, I will just substitute x equal to z plus z bar by 2 and y equal to z minus z bar by 2i. So if I do this substitution, and rearrange it, I will get something of this form. So after substituting, you will get this form, and alpha, gamma are real numbers, beta is a complex number. All right. So you will have the similar thing for lines as well. So if you do the same substitution, you will get beta z plus beta bar z bar. So again, these two equations over here, these two are quite similar, only in for the lines you will have alpha equal to 0. So a general equation So this will be a general equation. For the moment, just forget the point infinity. So these will be circles in C infinity. Okay. Now, okay. Okay, we will talk about something else now. So I will talk about Mobius transforms. So Mobius transform. So a Mobius transform is just a function of this form. Okay. So defining this, there are some issues because you can have 0 in the denominator. For example, when if d is this, then you will have a 0 in the denominator. Uh, uh, Okay, the numerator, when the denominator is 0, the numerator is non-zero, because that would give you AD minus BC is 0, which we have assumed to be not true. There are other cases to handle here when like C is 0 or A is 0, but you can see that if you work it out in those cases also it will be true. So so now what happened is, when the denominator is 0, the numerator is non-zero. So at those points like these, I will just define the function to be infinity. Okay, so what I will be doing is, this is like algebra of unity. Mm, so these will be some conventions I will use. 1 by 0 I will take as infinity. 1 by infinity will be taken as 0. These are the only two that will occur. 0 by 0 and infinity by infinity will not happen. Okay. So now, since our function is taking the value infinity, I cannot define the function on C. I can only define it on C infinity. So for the Mobius transform, for any Z in the complex plane, I will define it to be AZ, whatever this part. And I will also have to define it on infinity. So on infinity, I will just take the coefficient A and C, like coefficients of Z. I will just take those. The other ones I will leave out. Okay. So by doing this, by defining it this way, so this, so by doing this definition, this will happen to be continuous. Okay. You can verify when like Z goes to infinity, your thing will approach A over C. Okay. Okay. Next, so I can compose two Mobius functions, and so the composition rule over here is important. Um, so just a second. Okay. So take two Mobius transforms. I want to see how the composition looks like. So this will be A1. Okay, so this will be our composed function. Keeping this aside for a minute, look at these two matrices. So if you multiply these two matrices, you will get okay. So if you just compare these two, if you compare them, you can see that the coefficients here, they kind of match. Yeah, so composing two Mobius transforms is basically taking their coefficients and doing a matrix multiplication, right? So, so your Mobius composition is also matrix multiplication. And since I had that determinant of A is non-zero in the definition of Mobius transforms, I can also make sure A is invertible. Okay, let me write it. So you will have a 2 by 2 matrix A inverse, which will in turn give, so A inverse will give a Mobius map just by reading the coefficient. Then like composing them will give you identity. So implies so one corollary is Mobius transforms now are invertible, which makes M from C infinity to C infinity so Mobius transforms now, they are homeomorphisms of C infinity. Okay. Okay, let us now I will look at the gen. So wait, so mob plus will be the set of all Mobius transforms.
Karthik?
Yeah.
So in the definition of Mobius transform, we are assuming that A, B, C, and D, like the entries of the matrix,
Yeah.
are they like just like integers or like rationals or some numbers, like all the
For
numbers?
now they are just for now they are complex numbers.
Oh, A, B, C, and D are all complex numbers.
Yeah.
Okay.
So when you're saying that set up all Mobius transformation, you're just saying that all A, B, and C and D. You mean
Yes.
there is no equivalence in between them for now on. When you are mentioning the Mobius plus group.
Yeah. There is no equivalence right now.
Okay.
Okay. Yeah. So this Mob plus set, it is also a group under like I showed that you can invert each of them, and associativity will automatically hold because it's composition. So this Smoke plus, this is not just a set, this is also a group. So I can talk about generators of this group. Okay. So okay. So using using just elements of these two forms, we can get any element of this form. Okay. By using, I mean like composing these two things. Okay, this is one point. Next part is so I claim that using elements of using elements of these two forms, I can basically generate any element of Mo plus. That is, if you want, you can look at this. Okay, so each of these will give you a Mobius transform, and so the composition will be this, which is AZ plus B by CZ plus D for any ABCD with C not equal to 0. And C is equal to 0, it is just of this form. Okay. So what I have proved is so what is F? So F is this, G is this, and J is this. So what we have proved is those three elements generate the group here. Okay. So now we will see another important property of this, of Mobius transform. So recall that equation of a circle was this. Right, this was equation of a circle. What I claim is that when I compose this by one of my generators, it will still give an equation of the circle. So for example, so instead of Z, I substitute it by W plus A, where A is some constant complex number. I will get so if you simplify this, this will become okay. So again, if you notice, this is still an equation of a circle, right? It still has the same form. So alpha is still real number. This is still a real number, and these two are still complex numbers. Okay. So this was for Z plus A. Similarly, if you do for let's say if you do this substitution, you will end up with okay. Again, this is also a circle. Third one is you want to do this substitution. So you will have alpha by Z. So if you simplify, this comes down to again a circle. So proposition so what do I mean by invariant? I just mean that every element of mob plus takes a circle in C infinity to another circle in C infinity. Okay. So proof is so since these three maps here generate our Mobius group, all elements of the Mobius group can be written as a like composition of these three. So since these three preserve circles, so any element of Mo plus will preserve circles. Okay. Okay, I guess I will stop here today. Okay. Are there any questions? Okay. No questions. Okay.